Hello friends, today we prove Euclid's theorem, which states that there are infinitely many primes, or there is no end of the sequence of primes. That is, this 2, 3, 5, 7, 11 continue somewhere 10,007, again continue. This sequence of primes never end. The sequence of primes never end. Now let's say its proof. We prove this by contradiction. So let's prove this by contradiction. So suppose there are only finitely many primes. Suppose there are only finitely many primes. There are only finitely many primes, say P1, P2, continue up to Pn. So there are only n primes, P1, P2 up to Pn. Now consider a natural number. Consider a natural number capital N, which is equal to P1 into P2 into P3 continue into Pn plus 1. So product of these n prime numbers plus 1. Now note that this number n, note that it is guaranteed greater than P1, P2, P3 up to Pn. Note that this n is greater than Pi for I is equal to 1, 2 up to n. So n is greater than P1, n is greater than P2, n is greater than P3, continue up to n is greater than Pn. Next we prove Pi does not divides n, and this is for I is equal to 1, 2 up to n. So P1 does not divide n, P2 does not divide n, and continue. So on contrary, suppose Pi divides n for some I may be 1, maybe 2, maybe n. Number 1. So Pi divides n for some I. This is sentence number 1. Now since Pi divides Pi, this implies Pi divides P1 into P2 somewhere Pi continue into Pn. Now why this is? Because if A divides B, then A divides B into C for C belongs to Z. If integer A divides integer B, then integer A divides B into any integer C. So Pi divides this product P1, P2 up to Pn. So this is number 2. Now from 1 and 2, we get this pi divides. Now in 1 pi divide capital N, and in 2 pi divide this product. So this pi divides N minus this product P1, P2, continue up to Pn. And again this is because if A divides B, comma A divides C, then A divides B plus or minus C. Okay. Therefore, Pi divides N minus P1, P2 up to Pn. Now this difference N minus P1 into P2 up to Pn, this difference is equal to 1 because value of capital N is this product P1 into P2 up to P3, P1 into P2 continue up to Pn plus 1. So N minus this product is equal to 1. So that is Pi divides 1, which is contradiction. Why this is contradiction? Because Pi is a prime and this prime number is greater than 1. It cannot divide 1. So Pi divides 1. This statement is not correct. Therefore, what happened? Therefore, Pi does not divide capital N. Therefore, this Pi does not divide capital N for I is equal to 1 to up to N. That is, P1 does not divide N. Okay. P2 does not divide N. Continue. Pn does not divide N. Okay. Therefore, divisors of N are the only 1 and N itself. 1 and N itself. Therefore, N must be prime. And which is contradiction to our assumption? There are only finitely many primes. Actually, this N is a prime and N is different from P1, P2, P3 up to Pn. That is, N is greater than all these numbers and N itself is and N is a prime. And therefore, there are infinitely many primes. Okay. Now see once again. Actually, to prove there are infinitely many primes, let's prove this by contradiction. Suppose there are only finitely many primes, say P1, P2, P3 up to Pn. Now using these primes, consider a natural number capital N, which is equal to product of this prime plus 1. Now note that this N is greater than Pi for I equal to 1 to N. Next we prove Pi does not divide N. That is, we prove P1 does not divide n, P2 does not divide n, continue up to Pn does not divide n. Now on contrary, suppose Pi divides n for some I may be 1, maybe 2, maybe 3, maybe n. Now note that Pi divides n, Pi divides Pi, therefore Pi divides P1, P2, continue up to Pi, continue up to Pn. And why? This is because if A divides B, then A divides B into C for C belongs to Z. Therefore, Pi divide this product. Now from 1 and 2, in 1 we have Pi divides N, and in 2 we have Pi divide this product. So Pi divides this difference, N minus this product. But this difference is 1. Now why 1? Because N is equal to this product plus 1. So prime number divides 1. This is not true. So we got contradiction. And therefore, this our assumption Pi divides n for some I. This is wrong. So Pi does not divides n. So P1 does not divide n, P2 does not divide n, continue, Pn does not divide n. So divisors of n are only 1 and n itself. Therefore, by definition of prime number, n itself is a prime number, which is again contradiction to our assumption there are only finitely many prime numbers. Therefore, number of primes are infinitely, or there are infinitely many prime numbers. Thank you.